Forgot to start recording. All right, now we're recording. So start simple, one dimension, no absorption, and we're going to add in one other thing, and that is we're going to say that there's also no dispersion. We haven't learned what that means. That just means that waves of all frequencies have the same velocity. And of course, once you start talking about different frequencies having different velocities, then you get all kinds of really interesting behavior going on. But we're going to start off simple. So one dimension, mathematically simple. So the other thing is these last two, these things together, if we combine them, then what that means is that our waves will keep their same shape. They won't, as they move along, they're not going to morph and change their shapes. And then, of course, that implies that once we start to relax those simplifications, that we can start to see things that are going to be changing their shape. And we'll learn all about that too. So besides being like, useful and important for, electrodynamics and optics, a lot of the math that we do here, we're going to emphasize skills that you can use for all kinds of other types of waves. And so things like looking at absorption and dispersion and the properties of waves related to those are going to be very much useful in all kinds of other wave equations, all kinds of other wave behavior. Again, our wave is some kind of disturbance in a continuous medium, and it propagates along. So it's kind of moves itself along. The disturbance creates a new disturbance ahead of itself, and that keeps going along and along and along. So we're going to go over stuff, tools for talking about our waves to begin with. And we're going to start off not even talking about electromagnetic waves. Let's start off just looking at waves in general. In general, what we're going to do is have some sort of shape for the wave. And so here, let me switch over. Oops, wrong button. So let's say that is traveling in the z direction. So I'm going to call that f of z right there. And the actual wave, the actual disturbance, is we're going to call that a little f, right? A little disturbance is going to be, oops, wrong tool. And it's going to propagate along in the z direction, but it's going to evolve with time. So I made a function of z and t right there. So we're going to start off at t equals 0. So here, our initial conditions. So f of z, so little f at time 0 will just be, hey, let's start with the shape of that wave. And we're going to see how it propagates along, right? And so we're going to say here is that it's going to keep its shape. And it's going to move with the speed that we'll call v, right? So how do we do that? Well, we can say that this disturbance, little f of z and t as a function of time, is going to be equal to whatever it was at time 0, but somehow we have to make it move to the right with speed v. And so the way we can accomplish this, right, is it's going to be f of z, but we need to shift it to the rightwards by some distance, v times t. And so to shift it to the right, we subtract off the distance by which it's shifted inside the argument. So it's moved over a distance vt, So it's going to be f of z minus vt. And so that's that same shape again. So we can just call that a capital F right here. And it's, excuse me, it's the same shape, but it's been shifted over. So again, we can write this right here, z minus vt. Right. So effectively what we're doing is we're just taking it and we're sliding it along rightwards at speed v, and that's what mathematically that z minus vt in the argument does. It shifts. It's effectively like shifting the axis along. So what we're going to do now is we want to keep these things together. In order to just have it slide over, we're going to keep this z minus vt together. And so I'm going to define a new quantity right here to make that simple to write. And I'm going to use a cursive z. Again, three bars. Yeah. So how far is the wave shifted over? It's shifted over a distance vt. So the speed is v. Right? And so this is that disturbance propagating at a constant speed. Cool. So if we do this then, right, what we've got right here, here, I'll point this out, right? Take the left side right here and the right side here now with our new variable, cursive z, and we'll take those two and here, let's take that down here and this down here. So what we're saying is the wave, the disturbance at some time t, does it look like? It looks like the shape, right? But I'm now using a variable that slides along to the right, f of cursive z. So I described it, but here, I'll type that in for our notes. Cool. So to see how we can, so right now this is just some arbitrary function. It could be the kind of thing we think of when we look think about a wave, but it could be some weird, just lumpy pulse or some other thing like that. Let's take a look at how it behaves. We've seen that like the language we talk now is differential equations. So let's take a look at the behavior of this with time. And that's going to tell us something. And we're going to relate the time behavior to the spatial behavior is where we're eventually headed. So let's start off, oops, wrong tool again. Let's start off taking a look at the time derivative. How is it changing? Well, okay, that's going to be the same thing as taking the time derivative, partial derivative of this shape, right? And this was, again, f of cursive z, though. So, well, okay, we don't have time explicitly in there, but one way we can do this is we can use the chain rule, right? So to take the time derivative, that's the same as taking the derivative with respect to z times the derivative of z with respect to time. Cool. And then we know what that second derivative right there, second in order, not second order. The second derivative in the product, that dz dt, well, if z is just z minus vt, then we'll have a fact that'll just produce a minus v. And then we don't know anything about this shape, so I can't say anything more than to leave it like this. It's completely arbitrary. And again, because I know where I'm going, we're going to take a look. Well, okay, that was the first time derivative. Let's do the second derivative too. Okay, and so, well, v is a constant, so I can just leave the minus v out front, and then we get d dt of this. Um, okay, and we can actually reverse the order of derivatives if we want. So we can write this as d dz of df dt, which we already calculated above. So um, that was a minus v was the d big F dt. So we can pull that out, and we'll get a minus v times a minus v gives us a plus v squared, and then what we're left with is the second derivative of big F. Okay, well, so what? Let's try to actually understand what that derivative with respect to curly z is going to be. We know that our shape with respect to our shape as a function of script z right there is playing the same role as freezing time, having f as equals 0. So we can do a few substitutions. D big F dz equals d little f d regular z, and then take the second derivative too. All right, so now we can make this substitution right here. So we've got, whoa, pardon me. Give me 1 second. Pen went crazy. All right. Yes, Harry's got his hand up.
Yeah, so I have a question how you got that second equation that you just wrote.
Uh, the second derivatives there.
Yeah, so up above it seems like there's a v squared term running around. Does that disappear somehow? Did I miss something?
Oh, you mean this stuff right here? We're going to substitute this.
Yeah.
This is a little aside. So here we'll put so here this is just we're just preparing to make a substitution. So let's make that substitution right now, actually. Right. So it's a little bit tricky because we're working kind of with 3 different variables and 2 different functions. Our 3 variables are the spatial distance, spatial coordinate, our time, but then also we've got this sliding spatial coordinate, this cursive z. So if I can substitute that in now for what was on the right. So, and that's why I kind of tried to inset that a little bit. And this is kind of nice because we've gotten everything now in terms of our disturbance, right? Our disturbance, its second derivative is equal to v squared times its second derivative, but again, second derivative with respect to time is equal to v squared times the second derivative with respect to space. You look at that as we try to remember this, and actually before I go anywhere, we often write this a little bit differently, just basically move the v squared over to the other side. So here I just switched left and right, but moved the v squared to the other side. And you can remember this because you can just look at it and do a bit of dimensional analysis. Oh God, give me 1 second. I just crossed out my whole thing. Here, let's do this. All right, taking the derivative is like dividing by that dimension. So the second spatial derivative is whatever the dimensions of f are divided by position squared, length squared. And then over here, this is f divided by time squared. So if we multiply by length squared over time squared in the denominator, that cancels out the time squared. And again, I left out the squared there. Cancels out the time squared, and we're left with a 1 over length squared. So we've got f divided by length squared on the right, and the same thing, dimensions of f divided by length squared on the left. And so this thing right here, right, we made no reference to electric or magnetic fields. So this right here is the wave equation. It works for all waves. So, waves, mechanical waves, waves on string, sound waves, we can describe water waves. We can describe them with this kind of equation. There's one little thing right there. We can actually, because we've got v squared, that would actually work for plus or minus v. So plus v was the thing moving to the right. If v is a positive number, then minus v will move it to the left. So actually, we can have both rightward and leftward moving solutions. And one of the things we know that from differential equations like this is that they're linear. So if you've got one solution and then another solution, a linear combination of them will also be a solution. So I could write our disturbance, in fact, right, we could have the rightward moving shape would be a solution, z minus vt, like that. But we could also have a leftward moving shape with z minus a negative vt, so that's plus vt. So the R and the L stand for rightward and leftward moving shapes. And so again, we can take linear combo. Basically, any kind of disturbance will work. Mathematicians will talk about, about some of the boundary conditions you might have to have. You want it to probably go to 0 or at least stay bounded as you go very far away. Things like that. Otherwise, you end up with violations of energy. You get infinite energy and stuff like that. But basically, any function we have, so long as it satisfies this differential equation, so slides along, and so you can just take a shape and make the argument z minus vt or z plus vt, and that will work. This important thing, once we start dealing with different frequencies and stuff like that, this fact that different linear combinations work is going to be really, really important. So here, I am actually going to take a snapshot of this, and then we'll start some more and talk about some other stuff, what to do with this. Sorry. All right, let me grab a snapshot. Cool. Sorry, I'm knocking stuff off my desk here. Okay. Any questions before I keep going? So wave equation, really, really important. All right, so what we're going to do right now is we're going to actually take a look at sinusoidal waves because you can build any shape out of a sum of sinusoids. And when I say sum, really I mean integral. All right, and so if we're talking about a sinusoidal wave then if our equilibrium is 0, so no disturbance, then we can describe them with 4 parameters. So I'm going to write this out. All right, so let's write out the function. So our disturbance now are f of zt. We're going to write it okay. So let's get so we can understand what these things are. So I'm actually going to make a little table with the different parameters. So start off with this very first one, A. That's our amplitude. Right, and so if I make a picture of my sine wave going along, and here's 0, and let's make, oh, not quite the top, a little bit off to the side. So first of all, that right there is our amplitude. Does this look kind of familiar from Fun 2? Give me a thumbs up, or not a thumbs up, an agree. Thumbs up. Yeah. Cool. Surprised. Okay. Cool. So then here's the next thing, the whole entire argument of the cosine. So I'll write that. So this k times z minus vt. We call that the phase. Right? Basically, where in the argument of the cosine. And then that delta right there, though, we call that the phase constant. Right? And so that right there will tell us, be related to how far left or right we shift this. It's not going to be exactly equal to delta if this is a function of, if this is z right here. Right? We would have to convert delta into a position shift based on speed. And speaking of which, v is our speed. Right? How quickly it's moving along to the right. So there's one more. So the I said 4 parameters. Right? There's one. There's this one. So our 4th parameter is going to be k. Whoa, I'm sorry. I don't like the way I was writing that. Cool. So this one may be new to you. Did anyone see this before in Fun 2? Or in a situation other than Fun 2? Think about lasers and atoms. Seen it somewhere. Yeah.
I've seen it in the physics of music class with
Physics
Dr.
and
Milne.
music. Okay, cool. Yeah, most definitely. All right. So here, let's write down what that is. So we call it the wave number. It's 2 pi over lambda. And what is it? It's kind of, oh gosh, I don't like what I did there at all. What does it do? It is kind of like, so if lambda is how far you have to go, this is, well, the reciprocal. So it's how often in space does it repeat. So we've got a name for that. So it's the, except there's that factor of 2 pi. So this is the, it's called the wave number, but the role it plays is it's an angular spatial frequency. Right? How often in space does it repeat? But then you got to multiply by 2 pi to get it into radians. And yet, remember our lambda, right, is our wavelength. Which is kind of like the period, but spatial, right? So how far do you have to go for it to repeat? So for example, from one crest to one crest, that's going to be lambda. There. So we've introduced another parameter, lambda, right here, which isn't one of the 4 that we have in the way we've described things here, but we can rewrite k in terms of lambda if we wanted to. We could substitute a 2 pi over lambda. So there are other parameters we can also use to describe the wave, but they are they can be obtained in relationship to other things from the wave. So for example, right, we can talk about a temporal period too. So t, right? So that's our period. So how long do you have to wait while sitting at a certain point before the wave repeats again? And we can also, related to that, we can talk about omega, which is our angular frequency. And so we can relate these, though, to some of the other ones. So omega, actually, we're going to write that. We're more used to thinking about a regular frequency. So omega is in radians per second. So that's 2 pi times our regular frequency. So I'm going to use a nu instead of an f right there. And then another way to write that, though, is this is 2 pi over our period right there. So this one right here is the frequency. So let's put a box around that. Why do we have all these different frequencies, you might wonder? Well, okay. And why do we have all these different periods? Well, it's not much fun to have stuff in the denominator, so we often don't work with the period that way. The other thing is while we think about a wave moving in space and time, we could also, instead of thinking of it as a signal in time, we can also think of it as a bunch of different frequencies. And so that is a useful way to look at it. But then why do we have 2 different frequencies? So there's the regular frequency measured in hertz, so 1 over seconds. That's what we measure in the lab. That's great. But it turns out, as you're doing math and stuff like that, our argument of our cosine, right, our phase goes from 0 to 2 pi, and it can keep going after that, but we really only care about it modulo 2 pi. So we're always going to end up multiplying that by 2 pi. So when you're writing stuff on paper and doing calculations, it's just a lot easier to work with omega. So here. If you're doing theory, doing calculations with paper, much easier to work with omega. But if you got some instrument that to measure frequency, it's going to measure regular frequency, not angular frequency. So you got to do conversions back and forth, and that 2 pi, it always ends up messing you up, messing people up. Like I said, I've seen Nobel Prize winners get confused where things are different by a factor of about 6, and why? Oh, I forgot to put in that 2 pi, right? It happens to everyone. But it's just we have to go back and forth between them, just no matter what's more useful at the time. So one more. Oh, so we can relate nu to omega and t, but how do all the omega and t relate to all the other parameters, though, right? We haven't talked about that. So how do they relate to the other 4? And so here's the relationship that we can use. Our frequency is V. Whoa, what am I doing? Sorry. Jumping ahead. V over lambda, right? That's useful. Cool. And that is one of these equations, definitely like really important in physics. I don't memorize it though, right? I just remember it by dimensional analysis. You've got 1 over seconds, 1 over time. You've got length per time, and you got length. And so you can figure out how to put it together just by dimensional analysis. So here's another way to relate these things, though. If you write omega is 2 pi, yeah. What do I mean by paper? Paper doing calculations. So when you're doing your work, like basically you don't want to work with nu when you're solving problems. You it's just going to be so much more convenient to work with omega. Then when someone says, oh, and this microwave is a frequency of 2.4 gigahertz, then when you go to do calculations with omega, you have to remember to multiply that 2.4 gigahertz by 2 pi. But until you're talking about actual, so omega is easier to work with. Why is it? It's because it's already in natural units of cosine, watts an argument, and radians. That's really what it comes down to. It'll be much shorter. All right, so if our omega is 2 pi over nu, and nu is equal to v over lambda, so omega is equal to 2 pi over lambda. Oh, and let's regroup that 2 pi over lambda here. I'm going to actually, let me just do one thing quickly. I'm not sure that you'll be able to follow this quite so easily. Let me write this again. So this is, why is the lower left, what is that? So this is on the lower left. That is a nu right there. So my nu's got a little tail off to the left, and it kind of bends. And then v over lambda. So how often does it repeat? So like 1 over seconds, meters per second divided by meters will give us 1 over seconds. So I'm just going to rewrite this here, 2 pi nu, which is equal to 2 pi v over lambda. And then I can just shift this, so it's a 2 pi over lambda v. And we know what 2 pi over lambda is. That's just k. So actually, this is another useful way to write this. Omega is equal to k times v. So, cool. Bunch of useful things there. So now, if we remember that we had, the right moving wave, which was kz minus vt, and we had the left moving wave, which was kz plus vt. We can rewrite these things over here. We can rewrite this equation here. And so, so if we look up here, this k times v right there, another way to write that is kv is, that's omega. So I can rewrite these things. So I can talk about a right moving wave. I'm going to distribute that k. So it'll be kz minus kvt, which is the same as minus omega t, plus delta. Right? So this one right here, right, is, it's moving to the right. Gosh. And then I could write the same thing over here. Not the same thing. Let's make it something that moves to the left. So same wavelength, so same wave number, but if I make it a plus omega t, that's k times plus v. I mean, k times a minus v, because it's minus her. So this here corresponds to a v less than 0. So this is a leftward moving wave. All right, so we've got tools now for describing our wave as it goes along. Oh, I had prepared something to show you all. An example of this. This is what happens. I'm out of sorts doing this. Here, I'm going to take a snapshot of this, and then I'm going to share a screen with you. Give me 1 second. Okay. Yeah, let me see about, what does the bottom right orange say? It's supposed to say leftward. So when I say right and left, that's the direction that the wave is moving. So, yeah, my apologies for the clumsiness of this medium. Here, I'm going to share Mathematica screen with you if I can. Application window. Okay. Let's see. Can you see that now? Do you see some Mathematica? Oh, yes, there you go. Now it's come up. See my Mathematica? Yes, cool. So what we've got right there is a, see, nope, that doesn't work. So at the top, aspect ratio is going to be weird just because it's a stream of different things. Can I make it look bigger? I don't know. Probably not worthwhile, but let's see. No, I don't know. I don't know how to, oh, here's the zoom. Okay. I can, yes, and other people can zoom in on their own computers too. So my function, the input one is e, that's what exp is, so like the base of a natural log, e to the minus x squared. And so I just plotted that shape, all right, and you can see it's that lumpy thing right there, right, this bell curve. A Gaussian is the name of that right there. And so then down below, I'm plotting that same shape, but instead of just sticking an x, I'm doing x minus vt, right? So here's what happens if we start to let time pass. Oops, I tried clicking on the shared screen instead of the application. So start letting time pass, and what happens? It moves along off to the right. Cool. And we can bump up the speed. So again, the important thing is this x minus vt right here. Bump up the speed a little bit, press play, and yeah, it's going to zoom along a little bit faster. And sure, even faster still. And we can take this and turn this all the way down to 0. Nothing's happening. Well, yeah, because the speed's 0, so it just sits there. Let's do one more thing right here. So we'll have it going off this way. Doesn't help to leave time frozen and let the speed change. Helps to let time go by. All right, so it's going along, and then it starts over when the time resets. I'm going to go back up here, and let's change the sign right here, though. Reevaluate it, and give it v going like this, and start the time going, and what happens? It goes off in the other direction when I change this to a plus vt. Cool. So nothing like profound, just wanted to show you that we could do this for this function, but if I wanted to, I could change it to some other function too. So we could just, here, let's not, oh, I forget how to, yeah, anyways, you can stick whatever function you want in there, right? We can make it x squared and see what happens to it. So here, let's just do this. Minus x squared plus 1, right? Go like that. Here's this. Here's this. Actually, let's make this a minus. So once I press play on this down here, same thing. It just keeps moving off to the right. Why did I choose an exponential? Exponentials are nice because they go to 0. Their equilibrium value is 0. They die off as you go along. So yeah, it starts off up here, goes down like that. It turns out that once we get into dispersive waves, so waves where different frequency components have different speeds for one particular dispersion relationship, basically like the dispersion a free particle encounters in quantum mechanics, a Gaussian wave packet. So we call these packets right here where it's a wave that like is nothing and then it grows and gets smaller. It could have oscillations in the middle, but it's sort of localized. A Gaussian wave packet like this maintains its Gaussian shape in the dispersion equations you see like in quantum mechanics. So it's just a nice one. It's one that comes up. Why did I choose it? Beyond that, nothing. It looks pretty. But notice that it is definitely not a sinusoid right here. So we can make this, though, out of a bunch of different sinusoids, a bunch of different cosines with a bunch of different frequencies. And if you've got a whole continuum of frequencies, as you start to get farther and farther away from zero, they'll get more and more out of phase. So they'll have positive and negative components all adding together, which add out to zero, right? And then in order to get the right kind of shape right here, though, you have to have the right superposition, the right amplitudes for all those different cosines. So same rules. We can do everything that we did with cosines. We can use that and make up one of these other shapes, wave packets. So here, let's take a look at a little bit of that. So I'm going to close this out. Oh, easier to go back to the whiteboard here. Cool. So yeah, so I mentioned that if the wave equation is linear, so it obeys the principle of superposition. So this idea of principle of superposition really useful. Occurs a lot when you're dealing with solutions to differential equations, which is a big part of physics. So occurs for our wave equations, occurs in quantum mechanics. This is what allows us to add together, to see what happens in the presence of a couple different charge, in some complicated charge distribution. We can break it up into individual, the effects of the individual pieces of that right there. So if you've got, this is going to only be true, though, for linear media, right? So we can have nonlinear media where the effect of having two different waves will also have some sort of interaction, like it might depend on the square of them or something like that. But in general, right, if we've got whoops, that's supposed to be an I. If F1 and if we've got both of these things, I keep hitting a button on my pen, sorry. That's supposed to say present. Right. Right, as simple as you could get, but it doesn't have to be that way, but this will certainly make life a lot easier. So let's do something with that. Let's take a look at two different waves with the same wave number and same angular frequency. Right, so we'll do F1. So it's got one amplitude. And yeah, so a non-linear medium. So the people who well, so first of all, right, remember so for E and M, remember when we were talking about polarization, and we talked about linear media where the polarization is just proportional to the electric field, but you could also have it proportional to the electric field squared or cubed or something like that. And I mentioned that, I've got in my lab, I've got a non-linear crystal. So you send a little bit of light in, one laser in, and it'll produce, so you send in a violet light and it'll produce a little bit of infrared light. So some of that violet light gets converted. And so suppose I send in a second beam, or better yet, I just double the power of that laser. You would think, okay, well, you should get double the amount of infrared light, right? Because you could treat it as having disturbance 1 being the original amount, and then wave 2 being another wave with the same amplitude, right? And so you should just get some disturbance that's twice what you had coming out. And it turns out, no, what you get is something that's going to be 2 squared, so 4 times as big. Right? So you can have nonlinear crystals, for example. The behavior of a spring that doesn't have a uniform spring constant, right? If the spring constant changes with space, so you take your spring and you hang 20 grams on it and it extends in a little bit. You take off the 20 grams, put on 30 grams, and it extends, a different amount. If you put 50 grams on it, though, it will not just extend the sum of those two things. It will extend some other amount, because K, as for example, the spring gets weaker as it stretches a bunch, so it starts to deform. So those are some examples. Kind of complicated, right? So that's why we're starting not with those. We're ruling those out to begin with. We will certainly come to more, though. So, okay, we've got cosine. So we're just going to call it K, though, common value of K. I have to rotate my hand. So same omega, so I'll just call that omega, but this has one phase constant. And then our other, no, sorry. Trying to not write on a slant. Okay, right? So now we know just from looking above that the total wave is going to be the sum of those. All right, so who wants to add those together? I'm not getting a whole lot of people volunteering. So how would you go about adding these things together? Yeah. Harry.
So mathematically, you could just say F equals A1 cosine of KZ minus omega t plus delta 1, and then plus A2 cosine KZ minus omega t plus delta 2. Although I don't know if that would be any help in actually visualizing what's going on.
Right, okay, so we added them together. But yeah, you want to visualize it. Somehow you want to, can you reduce that? Can you combine those or anything like that? Well, yeah, if they had the same amplitude, you could do some sort of crazy trig identity, right? If you've got a cosine and another cosine that looks like one of those angle addition identities or something like that. Who wants to do that? Not me, right? I certainly don't. So it turns out that it's a lot easier to do this if we use complex notation. Oh my goodness. I'm sorry. I left this thing on in case someone was having trouble logging on, but okay. Pardon me. So yeah, big pain. So what I would like you to do is we're going to use a mathematical technique that works, that makes life a lot easier. Cosines are nice. We're familiar with them. We can visualize them nicely because we're familiar with them. But it's going to be a lot easier to do this in complex notation. So here, let me just really quickly put up a poll. So how familiar are you with complex numbers? Okay, let's run this. Here's a poll. Okay, cool. So we've got one person who said, you know, really a lot, and then everyone else is little to barely. What I'd like to do is I've got some like review on complex numbers, and we're going to do that right now. I'm sorry. So what we're going to do now is let's do a little bit of review and practice, and this is going to run over into the next class. I can see right now because we are just about done. So actually, yeah, let's pull this up. So I'll actually screen share, but you can get this from Blackboard as well. So let me just grab this thing right here. So on Blackboard under resources, I've added one about complex numbers. All right, let's go over share. Cool. It should come up momentarily. There we go. All right, so we're going to take a look at complex numbers. I'm doing this with numbers here, but we're going to very quickly change into functions, right? So I'm going to represent my complex functions with Z, and when I need to have another one, a W. So there are really two different ways to write our complex numbers, two standards. So Z, we could write it as a real part plus I times an imaginary part right here. Or we could write it as our complex numbers got some modulus. That's what this absolute value, it's an equivalent, right, but it's a generalization of the idea of the absolute value. So we'll come back to what this modulus is. We can think of it as like the magnitude of a vector even. And so modulus times e to the I a phase right here. So it turns out that these two things, these two ways right here, are equivalent to two different ways of graphing things, right? We've got a real and an imaginary part, and so we can graph those as being like an x and y axis. So the first version right here is a lot like Cartesian coordinates. And then the second one, we've got a magnitude and then an angle. That looks a lot like polar coordinates right there. And I'm going to scroll down to a graph right here. So the real axis, we make the horizontal axis. The imaginary axis is the vertical axis. So again, we plot Z is xy, or real of Z, imaginary of Z, right? A plus IB, real of Z plus I times imaginary of Z. Or we could also write Z is equal to modulus of Z, so that's this magnitude of the vector, times e to the I theta, where theta is the angle at which we're plotting it. Yes, Harry.
Why e to the I theta?
Yeah.
Why the power exponent of e?
Yeah. So this is one of the most important results in math. So e to the I theta, we can write that as cosine of theta plus I times sine of theta, right there. And so sometimes that's abbreviated as cis of theta. So there are a bunch of different ways to show that. One way is to write out the Taylor expansion of cosine, the Taylor expansion of sine, and write this out, and what you get is the Taylor expansion for e to the I theta. There are other ways to do it that don't involve infinite series, but involve like several steps. So yeah, super elegant. Cool. And so notice right here, if I scroll back down, right, cosine of theta, well, that is the horizontal part of this triangle. Sine of theta, if we're up to a modulus times modulus of z. So z times sine of theta right there, sorry, modulus of z times sine of theta gives us this vertical part right there. So in our e to the I theta right here, right, we could write this as z modulus times cosine of theta plus z modulus times I sine of theta right there. And so z modulus cosine of theta is the real part. Z modulus times sine of theta is the imaginary part right there. And right, we know that cosine squared plus sine squared is equal to 1. So if we've got a modulus out front, right, we can rewrite it right here. So the modulus of z, or modulus of z squared, is real part of z squared plus imaginary part of z squared. So the modulus of z is the square root of that. And again, from our graph, if I jump down to here, right, if this is the real part of z, this is the imaginary part of z, and we make those two axes orthogonal to each other, this is a 90-degree angle. So by Pythagorean theorem, we can get the modulus of z from the real and the imaginary part, the square root of the sum of their squares. Cool. So I actually want to stop right there. So we've introduced these ideas, the complex numbers. You can go ahead and take a look at this a little bit, although I think your time would be best spent, preparing homework, yeah, doing the homework and the chapter summary for next class. What we're going to do is, if you go download this PDF from Blackboard, there are also some accompanying problems, and we're going to work through those in class too, because it's going to be important to be comfortable with imaginary numbers. For this class, it'll also be really useful for quantum mechanics. So, cool. I'm going to leave it here, and we'll see you next time. Take care. All right. Everyone's leaving. See you.